About that time, my name's Elias Wooten. I hope Dr. Me introduced me like at least a little bit in the previous classes. I'm a master's student here. I did my undergraduate in computer engineering, graduated 2021, worked in industry for 3 years, and then came back from a master's degree in electrical engineering. So with that in mind, it's been like 6 years since I've used this program. I did a bunch of refreshing, but we'll see how it goes. Sounds like some stuff that I don't know if you know yet. Have you learned about diodes? I think that's the first thing you cover in this class, right? No, no diodes?
We're starting with the amplifiers.
Starting with amplifiers? Okay. Yeah, when I took this class, I don't think we covered amplifiers at all. We covered op amps. Are they op amps?
Yeah.
Oh, okay. You covered op amps in 210, right?
Yeah.
Okay.
That's why.
Sweet. I don't like op amps. They're okay for some applications. They make some stuff easier, but they're also just hard to understand. Well, I'm going to cover diodes. They're not super complicated devices, so I'll give you like the easy spiel of them. So then you haven't talked about BJTs or MOSFETs like at all, right? No? A little bit?
It's literally just been off ramps.
Okay, bet. Okay, so kind of follow-up question. I downloaded some kind of application so you can see my key presses at like the bottom left of the screen. But I don't think half of you guys can see that. So I'll try to avoid hotkeys, but in general, do you guys like hotkeys? Yes, yes. Does anybody hate hotkeys? It's like where you press a shortcut on your keyboard instead of having to use like the manual. Yeah. If you don't like hotkeys and you like using LT Spice, then you're a unicorn. Because everything in here is kind of awful with the mouse, but really good with hotkeys. I'll try and teach you guys some of the basic ones because it makes life a lot easier. Otherwise, you're going to be kind of fighting the program the entire time because you have to right click and then do everything from this. Survey. Can you guys read the text in the back? No? I got one yes, one no. You can see it. Okay. Let me see if I can make it bigger. I might just descale the resolution, but I don't know if that's actually a solution. All right, is that any better in the back? A little bit, maybe? Okay. I'll leave it like this. Cool. With that in mind, I'll start with like a really brief introduction of a diode, because that's kind of like what he wanted me to teach you guys. So to select components in LT Spice, the easiest way of doing it is like right-clicking, then going to draft, and then going to component. You can also see that they have like the hotkeys listed here. I might instinctively start using the hotkeys. If I do, just tell me to stop because you won't be able to see what I'm doing. But there's a few like important things to mention here. Spice directives. If you want to run a simulation, you have to have at least one spice directive. If you want to have like stuff on your diagram, you have to select it from the component list. And then the last really important thing to mention is the net name. You have to add a ground for it to run the simulation. Wires are kind of self-explanatory. It's how you connect all the components. So I'll start by selecting component. It gives you a big list. You can sort through it manually through the drop-down menus. I normally just type in what I want. So there's a diode. I can click. It'll prompt me to like continue placing more components, but I'm not going to do that for now. You can also click and drag in order to move the screen. If you have a mouse, I think you can hold shift and then the scroll wheel in order to get it to move left and right. And then if you scroll normally, it zooms in and out. But it's a really old program. The DPI of your mouse like heavily influences how the program interacts with it. So I tend to avoid the mouse when I'm using it. You can also just type in D to bring up a diode, which is very convenient. Same thing, R is resistor. I would probably L is inductor. Yep, L is inductor. And then V is voltage source. That's another one of the pretty big ones. But again, I'll just use the GUI for everything so you guys can see what I'm doing. Yeah. I guess another pretty big one to mention, if you have a component, you want to rotate it, it's not R because R brings up resistor, it's control R. I don't think you can do that through the GUI, so you'll just have to remember that. Control R to rotate. Yeah, so I'll just start like building out a circuit. Again, like slap me if I start doing stuff through the keyboard. So you're gonna need a voltage source, you're gonna need a resistor, and you're gonna need a diode for this like first little thing. If you want to follow along, if you have it downloaded, I'll go slower. Does anyone have it downloaded and plans on following along in class? Okay, a bunch of you guys. Sweet, you're in a good position.
It's wires.
To wires? Good question. Right click, draft, and then it's the top one, or you can press F3. Yeah. What's up? Rotate what? Oh yeah, control R. Yeah. There's a lot of simulation software that doesn't run on Mac and Windows. This is one of the nice ones that actually does. But there's a few that like it'll force you to do Windows. If you have a Mac, you can have like a PC at home and then remote into it, and then you can run all your simulations on the remote PC.
But it seems like the hotkeys are different or something.
Oh, for Windows?
Yeah.
Un-
HW for what? YSW.
Oh, really?
Yeah, we have.
Bummer. Okay. I'll try and teach you guys everything without the hotkeys then. If you want to learn the hotkeys, then it should just say in the drop-down menu. You definitely can't see this, but wires, it says F3. Hopefully, if you right-click, it says W for Windows. Does it?
Yes, it says W for wire.
Sweet. Okay.
Components are P.
Components are P. That's fun. Okay. So I'm just gonna wire up my components real quick. It's not super sloppy, but it's also not like the easiest.
It only does horizontal or vertical. You can't do both at the same time.
Yeah, no horizontal. There's some programs that where if you just go from one place to the next and then click, it'll route like right angles nicely. This one doesn't do that. It's unfortunate.
The big roots meet the wires, so.
Maybe. I haven't experimented with it, but if it does, then that's really nice. So what we're doing basically is characterizing our diode with this circuit. Essentially what that means is we're looking at the forward voltage versus the forward current graph. So in order to do that, it's going to make us hook up a resistor. We're just going to enter a really, really small value so that we essentially get the pure response of the diode. So I'm just choosing, what is that, 0.1 milliohms. You can choose a milliohm or you can choose less. All of that will like kind of look about the same. The next thing I'm going to do is I'm going to right click on my diode. And then I'm going to click the button at the bottom there, pick new diode. And then I'm going to pick this diode here. Basically the 1N series, there's 1N series of diodes, there's 1N series of MOSFETs, and I think there's 1N series of BJTs. I almost never use BJTs. I think they're all made by onsemi, and they're like the standard older technology. So they work for almost any application. If you're doing senior design or something like that, and they tell you to choose a diode for something, choose like the 1N something. And it like pretty much will act like your theoretical diode. Oh yeah, something else to note, I am screen recording. I'll share the screen recording and I'll share my notes with some resources for you guys to be able to do this on your own later. Hopefully you can hear my voice through the mic. Yep, so I'm going to select that. And then the next thing I'm going to do is I'm going to come over to my voltage source on the left. And I'm going to give it just some arbitrary DC value. I'll choose 10 because it's kind of a nice round number. And then once you have this, you would think you can just run the simulation. There's just two things you need to do from here. You right click, you go to draft, you go to net name. Sorry, I'll do that slower. Right click, draft, net name. I'm not sure what it is on Windows, but on Mac it's F4.
We don't have that name. We have labeled that.
Label net should be the same.
Yeah.
Does it have the option for the ground?
Yeah, it has,
Okay, that looks good. So you'll just select ground. Calm is different than ground. I think it'll throw a fit if you use calm instead of ground. So ground will be your best bet. So you select that. You'll put it at the bottom, essentially where you have your negative sign of your voltage source. It's all the same wire from the end of your diode here. I'm sure you guys remember that from 210. In real life, not so much in here, yeah. And then after that, you'll do one more step. You'll just right click, go to draft, then you'll choose a spice directive. Essentially, this is telling your software how to run. And you can choose a bunch of different things. You can choose AC sweeps, you can choose run for a certain amount of time, and you can, and there's probably other stuff that I don't know about. Pretty much all the directives start with a dot. So if you want to perform a DC sweep, which is what we're going to be doing here, just do dot DC. And then I have some notes over here, so I'm going to keep referencing this. Okay, yeah. So you do dot DC, and then you'll choose your target. My voltage source is named V1, so I'm going to choose V1. After that, you just add a space, and then you'll choose your minimum voltage. I'll show you negative voltages on the diode just so you can kind of see its behavior. So I'll just choose, and then I'll put another space, and then I'll choose my maximum voltage. I don't remember what it is for this diode, so I'll just choose 10. Then I'll add another space, and then I believe the last thing is your sample rate. So if you want more granularity to your simulation data, you'll choose a smaller number. It's a little counterintuitive. So if you choose 0.01, then that means you're gonna have so per volt, you'll have like the inverse of this many steps. So that would be what, like 10 steps or 100 steps or something like that. 100 steps. If you choose 1, it'll just give you 1 step per volt and your graph will look kind of funky. So I'll go ahead and put that in there. You can place this anywhere. Typically, people place it at the bottom. Sometimes people will place it next to the voltage source that it's commanding. Kind of up to you. I prefer it at the bottom. It leaves me space to do things in other parts of the screen. And then once you're here, you should be ready to simulate. So you can hit the little guy running at the top left of the screen, or
assuming it's the play button on Windows version.
yeah, probably. I thought it was a little running guy for both.
I did not see any.
Oh yeah, you guys got a lot of different buttons. What if you right click?
Or right click it on seems to be that run pause.
Okay, run will be your guy then. Does it have a little running icon or is it a little play button?
It's a play button.
Oh, okay. Okay, yeah. So on Windows, it's a play button. On Mac, it's a little running guy. You hit that, it'll pop up your thing, and it won't show you anything. That is intentional, because you haven't told it what you want to like look at yet. Yeah, so yeah, it's intentional. Once you get to here, then you can select voltage or current of the various components. We're gonna select both. If it gives you the little red like pointer with the squiggle coming out of it, that's a really old device. It's a voltage probe. Some of them even have lights, so when you poke something that has voltage, it lights up. But anyways, you'll literally never see that again. So you'll click it. Sometimes it'll give you effort, like a hassle. Then you'll see your voltage from your voltage sweep. So it goes from -2 volts up to 10 volts. There's really nothing of interest on the x-axis yet. Until you click the current. So the current essentially is a device that has like physically it's literally a device that wraps around your cable. In EE or not EE, Physics 196, you learn about the Hall effect. This is literally measuring the Hall effect of the device in real life. Then they just give you a little symbol that's supposed to mimic it. Do you guys care about these like facts at all?
No.
Okay, sick. So you go ahead and click that, and that looks kind of small. I'll zoom into it in a second, but can you see that blue line at all, or is it too dark on the screen?
On the screen, it's barely visible.
Barely? Okay. Well, you'll just have to trust me. There's a blue line.
Well, in fact, yeah.
Yeah, on the projector. In IRL, I'm assuming you can see it on your displays. Projectors are kind of trash tier technology. What's up?
How do you flip a resistor and
Yeah.
No.
When you before you place, so press R. Now control R.
Yeah, there's also a little hand. So if you right click and then you do edit and then drag, you can like pick up your components again and move them around. And then you can hit Control R.
We do not have drag.
You don't have drag? Do you not have move?
There is move.
Okay.
Yeah, and delete in the days.
Yeah, right. It should be underneath edit.
So it's right click. Yeah.
Okay. Yeah, so once you have this up, this is kind of an important part for me at least, because I'm going to be grading your guys' assignments. And if your graphs look like this and I can't see what's going on, it's going to make my life hard. If you want a good grade, make my life easy. Either you can zoom in by just like clicking and dragging and it'll move a box. Wow, you guys really won't be able to see that. Yeah, and it'll move a box around, you slide, and then it'll like enhance your image to like the section that you want. You can kind of see there's like a little bit of a curve at the bottom here, and then it's mostly linear. If you want to make it look even better, what you'll want to do is you'll want to like reduce the voltage of your sweep in order to like zoom in effectively on that region. So it stops at 2 volts. I'm just going to do -1 volts, and then I'm going to hit rerun. And then you can see it kind of like blew it up. It moved the curved section to like the center of the screen, and that makes it a little bit easier.
But you changed -2 to -1. That's what you did.
I turned -2 to -1, and then I changed 10 to 2. Yep. Yeah, and then how many of you guys are familiar with the snipping tool on Windows? Okay, pretty much everyone.
Big screenshot.
Yeah, screenshot. Sick. On Mac, it's Control-Shift-4, and it'll pull up your screenshot tool. I've looked for a bunch of different ways of actually just taking this and then saving it as a PNG or a JPEG. It doesn't exist. You can save it as a PDF, but you're still gonna have to take a screenshot of it anyways, and it'll put it into light mode, which is substantially harder to read in a document. So I prefer it if you just take the picture of the thing directly. Just make sure you get all the numbers when you do end up taking the screenshot. I've had some people with like some pretty bad cropping skills, and it makes it difficult to grade. What's up?
What's the text that you put on the text on some bad or the directives?
Oh, the directive, the text?
Yeah.
Yeah, it's just this guy. Yeah. Okay. Yeah, so that's pretty much like all you need to know in order to get to a basic graph. I'm realizing now I never really described diodes. that graph I just showed you is like the textbook graph that everyone's going to give you for being able to tell like how a diode reacts to forward current. So when current is passing through this way, you can kind of think of it as an arrow. The arrow means that you're going to be able to push current through it this direction. If you try to push current through in this direction, it's got this line that indicates that it's a block. You won't be able to push current that way. And if you think of current and voltage as like a relationship, that means if you try and push voltage this way, push current this way, and you put a voltage drop across the diode, then you're just constantly going to see whatever voltage you put here across it. But if you put current this direction through the diode, and you have like some kind of voltage divider, then you're going to be able to see the voltage change across the diode as you push more or less current through it. In the graph that I was showing you earlier, that's the interesting portion is down here where it actually curves. And then you have a pretty much linear region up here. And then you have from here back, you guys can't read these axes. This is 0 volts. Behind here is negative voltage across that diode. So like I was saying, you can't pass current up this direction through the diode. And then from here to here, before you start that curve, I don't really remember what they call that region, but essentially the diode just doesn't have enough voltage across it to begin throwing current through it. And then after you get to that to here, I also don't remember what this region is called, but essentially it's the nonlinear region of the diode. You don't really like playing with this region because it makes things difficult when you're trying to make an amplifier or use it for like a buck converter or something like that. You almost always want to be in the linear region. Exactly the same thing with MOSFETs and BJTs. You almost always want them in the region in which they react linearly. It makes your amplifiers better. If you're doing yeah, I guess literally just amplifiers. I don't deal with amplifiers, but if you're doing amplifiers, which is all you do in this class, you're going to want it in the linear region. If you're doing switching, you almost always want it not in the linear region because you're going to be losing a lot of power in the device, which means it gets hot and your efficiency goes down. You have to make your device larger, more expensive. Nobody likes that. Yeah. So that's pretty much it for this. This is literally your first stage of your first project. You do this in order to characterize the diode and kind of correlate it back to your textbook. So kind of take note, because this is what you'll be doing. So from here, we can move on to a more complicated circuit, but you guys haven't really done MOSFETs. I could talk more about the same concepts. We could talk about sourcing components on DigiKey, or we could talk about the rubric that I just created for you guys, which I'll release later today for the project. I guess show of hands, who wants to see the more complicated circuit? One, okay, like half the class. Who wants to see the rubric? A little bit more than half the class. Who wants to source components on DigiKey? That's also part of your project. Okay, like 10 people-ish. Yeah, it can be, but it's also kind of a pain if you don't know.
Is that just like downloading plugins to put in here to get more components or what?
You'll literally just go to the website, find a diode, and then do you know that library that I pulled up earlier?
Yeah.
You can find it in that library, or you can go backwards. You can find it in the library and then find it on DigiKey. What's up?
Sorry, I'm still a little confused, like how you like use like the basics of LT Spice.
Sure.
I'm kind of like, what's like the .dc v1? I know you went over it, but I'm still confused on it.
Yeah. I'll go a little bit slower. That's what they call the SPICE directive. Essentially, it's just telling your computer how to simulate the circuit. The .dc is indicating what kind of directive it is. So in this case, .dc means DC sweep. The next little value in here, V1, that's the target for the directive. V1 is the name of your voltage source right there. So what I can do actually is I can right click this. I think I can go to advanced and think I can rename it. Okay, no. So in order to rename it, you just right click the V1. So I'll call this DC sweep. And that's just the name of the device now. So if I were to run this, I think it would error. Yeah, so it's looking for V1, but I've renamed it to DC sweep. So it no longer exists in terms of its mind.
What if you have like multiple voltage sources, you're like,
Yeah, good question. Let me see what time it is. It's 9:55. We have like 50 minutes left. I'll get to the more advanced circuit and I'll show you what it's like with the two sources. Okay, what's up?
I mean, I have the graph displayed, but I don't have the right, like, lines.
Yeah, good question. I'm just gonna delete this graph real fast and then I'll come back and recreate it. It's gonna make me rename this real fast. Okay, there we go. Cool. So to get the stuff on the graph, if you want current, you're going to be looking, you're going to hover over the component that you want the current of. So in this case, I want the diode, and then you're going to look for this little guy that's got the like red arrow through it with the little circle. You see that one?
Yeah.
Perfect. So you just click it. Half the time it won't show up. I don't know if you can see that, but it didn't show up just then. So I'm gonna have to wiggle my mouse and then I'm gonna have to click it again. And then it shows up. I think that's just like a glitch. Windows might be better. Same one. It's the old program. I think it was literally made in the 90s. And then yeah, for voltage, it'll give you this little red guy. And then it showed up. You can barely see it, but there's a little blue line on the screen now. Yeah, of course. Yeah, any other questions before we move on? What's up?
What's going on with the axes? Like there's an axis on there's a current on the right, voltage on the left, and voltage on the bottom.
Yeah, good question. So I believe the bottom axis is gonna be the your sweep axis. Since everything here that we're measuring, meaning the diode and the voltage source, they have the same voltage. It looks like this axis and this axis are the same, and that's because they are pretty much. So yeah, this is your voltage source. And then this is the voltage across your diode. And then this one is going to be your current. So when I clicked on the diode and got the current, it painted it in green. And you'll just like have to keep track of that mentally because there's no way of correlating it after the fact. Oh no, that's not true. Right there, ID1 and then it's green. And then yeah, this will be your access for the current of that device. Okay. Does that make sense? Mostly. Okay. I think if you add multiple, more than 3, the axes do start getting confusing because it's gonna have to scale, like this blue line down. Let's say if you had a device that had like 10 volts across it. So I can show you how to mitigate that issue.
And the color is dependent on the order to choose these things.
The order you can change it.
I'm pretty sure, right? They did it in the opposite order this time, but.
Yeah, so it's not like green is current and blue is voltage. It's just the order that I selected it. And then you can change it. So if you want pink for that blue line, you can change it to pink. Blue and black don't have very much contrast, so if you want to change that, that makes it a lot easier. Yeah. Okay. Good. Chill. Okay. Awesome. So that's basically the first part of your project. The other thing that he wanted me to teach you guys is how to bias a MOSFET. So I'll go on to that. It's the more complicated circuit. Okay. You guys ready? Sweet. So I'm just gonna start with the voltage source. So I'm gonna right click, I'm gonna go to draft, I'm gonna go to component, and I'm gonna type in volt. Pulls one up. I'm gonna stick that on the left. And then I'm actually gonna have two. So I'm gonna just keep having it selected. I'm gonna put another one down, and then I'm gonna hit escape. That's gonna get rid of it. Then I'm gonna hit right click, draft, and then I'll just go ahead and choose the MOSFET for now. So if you type in MOS, it's not going to come up with anything. It's kind of annoying. What you're going to have to do is you're going to type in N and then MOS. There are two types of MOSFETs. There are N-type MOSFETs and P-type MOSFETs. You'll learn that in this class. If you're using them for switching, the only thing you have to remember is that N-type MOSFETs connect up to the top bus, P-type MOSFETs connect up to the top bus, and they're powered with an inverted signal. So if you give it a logic 1, then it won't flow current. But if you feed it a logic 0, it will flow current. NMOS are exactly the opposite. You connect them to your ground with the bottom pin, and then if you feed them a 1, it'll flow current. If you feed them a 0, it won't flow current. Show of hands, how many of you guys are computer engineers? Okay, a little bit less than half. So that change in what sends current through one of these devices is how you create logic. Yeah. So that's how you get like AND gates and OR gates and all that kind of stuff is with that difference.
So transistor.
Yep, transistor. Yeah, MOSFETs and BJTs are both transistors. So are diodes, technically. They're also transistors. I think the definition of a transistor is something like something that changes its electrical characteristics based off of inputs. Yeah. Yeah.
We're gonna get a.
Yeah, you're gonna get an NMOS. They're way easy to work with. I don't like other transistors very much. Yeah, so we're gonna select an NMOS and we're gonna put it here-ish. Next thing we're gonna pull up is a resistor in order to create an amplifier. And you're just gonna put that like slightly above your NMOS. You want a little bit of a gap here so you can collect the voltage data later. And that's it. We're just gonna wire it up now. So right click, draft, wires, and then I'm gonna connect everything to the ground. Then once I have everything connected up to the ground, then I'm gonna connect V2 to the gate of the MOSFET. Another important bit of information, I suppose, there's 3 ports on a MOSFET. You have the gate, which is going to be like your voltage input to the device. You're going to have your drain, which is actually at the top, and then you're going to have your source, which is at the bottom. And the reason why it's called that and not like inverted is because of the way that electrons technically flow. So when current flows through your device in this direction, the electrons are technically going the opposite direction. So this would be your source of electrons, and then it drains out the top, even though your current's coming from the top. Does that make sense at all? How many of you guys have had Barry Dorr for 210 or 310? Nobody? He retired, right?
Yeah.
Okay. Who do you guys have for 310? Have you done 310? Tong Huang? Did you like him?
Yeah, he's great.
Okay. Say. Yeah, Dr. Me might also explain that later. I'm not sure.
Some of us are still taking 310 currently.
Yeah, I did that too. It's not so bad. Anyways, yep, that's how these things work. Also, another kind of fun fact for the MOSFETs, they are diodes that you control the semiconductor material. So if you try and put current this direction through a MOSFET, it won't work. It'll only flow current this direction. With that being said, Here we go. This is a good picture. 99.9% of the time, when you buy a MOSFET, inside of the package, you're also going to have a diode that goes the other direction. The reason they do that is so that they blow up less, essentially. Because if otherwise you'll end up like putting a bunch of current through here, and then you'll have a little bit of inductance in your wires. You're just straight up have an inductor. And then you flow current through that inductor, you end up with a really large voltage spike on the inductor. And then your device will have way too much voltage across it. This diode allows the current to shoot back into your voltage source, and prevents it from blowing up. Anyways, so you can't rely on the fact that it doesn't always put current back up through it, but in LT Spice, I think all of the MOSFETs don't have that diode. I might be wrong on that, but anyways, yeah, let's add the wires for the drain of the MOSFET and the voltage source. Cool. And then on the voltage source on the left, V1, I'm just going to right click it and I'm going to say 10 volts. Again, it's a really easy number to work with. And that one's just going to be 10 volts always. We're not going to alter that with a spice directive. For V2, that's going to be the more interesting one. Again, let's right click it. Let's put that 10 volts in, but we're going to override that with a spice directive. Then I'm going to go to draft. I'm going to add in a spice directive, and then I'm going to do another DC sweep. What's that?
Can you just override it and
Put
the 10 and then override it?
I don't know. Yeah, sorry about that. Yeah, I would assume that you would be able to, but LT Spice is really old, so it might just throw an error. But if it gets overridden, why would you want it? .dc because we're doing a voltage sweep, and then we're gonna do V2 because we're not targeting the voltage source all the way on the left there. Then we can start with let's just start with 0 volts. And let's sweep to 5 volts. I think that's going to be a little bit. No, actually, shoot. Let's do 10 volts. I remember. I was doing this earlier. Yeah, so start with 0, go to 10, and let's do yeah, just .01. Decent simulation time, pretty good granularity. And hit OK. I'm going to place that like roughly underneath that. Okay, so there's something wrong with my circuit. Do you guys know what it is?
Are given to find a resistor.
There's no
Okay.
ground.
Yep, there's 2 things wrong, I guess. Good catch. Yeah, no ground, haven't defined my resistor. In this case, let's make the resistor a little bit bigger. Let's do 10 ohms. So that way when the NMOS is fully open, makes the math really easy. So 10 ohms for the resistor, and then, yep, good job with the grounding. So that would be net name, ground, and then you can just stick that like over there. Some PCB. I don't think you guys are going to design PCBs in this class, but you will eventually. Some general good practice. Don't put your ground at another node. It makes it difficult to discern if you meant to do that or if you didn't mean to do that. And in some programs, it actually becomes really difficult to tell if they're hooked up or not. So always try to keep like one node slightly away from ground. Same thing if you have like 2 resistors coming like this and then a wire that has to hook up to them, just slightly offset your resistors. It makes it like easier to tell what's going on. Okay. That looks good. I think we should be able to simulate it. Yep, didn't throw any errors. I'm gonna move this over here. I'm gonna move this over here. And then I am going to select my voltage of my voltage source. So this should just give me my sweep voltage. Here we go. And double check it. It goes from 0 10 volts. There we go. And then we're gonna look at the current through the MOSFET. So click that. I'm gonna change the color so you guys can see it a little easier. Maybe like red. There we go.
You put the voltage?
The voltage, oh, the voltage meter, it's just sitting right here. But now that you mentioned that, I think I don't want it there. I think I want it at the top of the MOSFET as well. That's my fault. I think you can just right click this. No. So there is a way of getting rid of plots. See if I can find it. Delete, and I want to get rid of the green one. There we go. Cool. Yeah, so you just right click it, then you go to edit, and then you go to delete. It looks like it's the same hotkey actually for the schematic editing and the graph editing, so that's convenient. And I'm gonna select the voltage between the resistor and the MOSFET. Yeah, what did I do last time? Hold on. So this is 10. This is going from 0 to 10. And I'm measuring the current. I'm just trying to figure out why the current here isn't that same S curve.
Well, your other was going 900 milliamps.
Amps.
Who goes from?
Yeah, so 1 milliamp versus 100 milliamps. This is 10 volts. This is going from oh, right. Okay, sorry, there's one more thing that I messed up on this one. If you don't choose a component for your MOSFET, I'm not really sure what it does, but it doesn't work. So pick the transistor. If you click on part number, it'll sort it to have the 2N7002. That's also a really good MOSFET. I would suggest using that one.
How do you change the component?
You'll right click it, then pick new transistor at the bottom.
And one. Whatever we were. That's what I've got.
Oh yeah, and then on the list, you'll click on part number. Good.
You don't see it too. It's on the phone. On the bottom.
It could be on the bottom or the top. Switch part number to that.
Yeah, I really wish this was like a search bar. I tried to find that for a while, but I couldn't find one. Got it?
So, the part number there, and then I think it can, yeah. And then Charles put on.
All right, good. Sweet. And then if we hit run again, there we go. Now we have our nice S curve. Then I'm also gonna get the voltage between the two. No, that's not what I wanted. Okay, there we go. I'm gonna right click, edit, delete, and then I'm gonna delete my
Where'd you get the red curve?
the red curve is the output of V2.
Oh, where did you get the curve?
The green curve is the current of M1.
So red curve.
Red curve is V2, voltage of V2. Yeah. Okay.
So, and where do you click to get the
very top of M1. It's like almost outside of M1.
Yeah, it's just like all the way up there. Yeah, you're basically clicking on the output pin of the device.
I'm not getting that aspect error.
What's up? How to get the transistor? So what you're gonna do is you're gonna right click it. You're gonna hit pick new transistor. Oh, you don't see the pick new transistor button? How do you get the pick new transistor?
If you look at the actual thing, they have a pick new MOSFET.
The actual thing? The
Instead of it saying pick new transistor, it's pick new MOSFET.
Oh, okay. Does it also have a pick new MOSFET over there?
Yeah.
Is it good?
Yeah, it's good.
Okay, sweet. So does everybody have this like little S curve
Yeah.
up? Everybody? Okay. So you know how I was talking about the linear region earlier? This is gonna be your linear region right here. When you bias a MOSFET and you want to make an amplifier, you're gonna want to be in that S curve. Specifically in the region of the S curve, which looks most linear. You can bias it here, but then when you like change this voltage, with like a sinusoid, you're gonna be moving like up and down this curve, and it's not gonna be it's gonna increase your harmonic distortion. Because when you try to go down a certain amount, it'll go down more than you or less than you expected. Similarly, if you were to like do it up there, then it'll go up less than you expect when you try and go up. So if you bias it right in the middle, then you can swing your signal all the way down here, and you can swing your signal pretty much all the way up to there. While still getting a linear response.
What do you mean when you say bias?
Yes, good question. Traditionally, when you're making a MOSFET amplifier, you're not going to just have a voltage source feeding the input of your device. You're going to have a sinusoid or a sawtooth or something like that instead of a DC here. You'll have a capacitor to make it so that no DC current flows. And then you're going to have a resistor here, and you'll have a resistor here. And you're going to try and get the voltage with those two resistors at this point to be right in the middle of that S curve. So
4 volts.
what is that right there? You would just draw it down. Yeah, so like you would take 4 volts, maybe a little bit less, maybe like 3.8, 3.9. Do you want me to show you what that looks like?
Yeah.
Cool. Okay, so what I'm going to do now is I'm going to delete this line here in order to put those resistors in. There you go. And then I'm going to just type in R, put in a couple of those, and then it looks like I have enough space. And then I'm also going to include a capacitor just to make things a little bit easier to look at. I'm trying to remember what capacitance you would want for this. I'm just going to say it's 100 microfarad. So that's 3 zeros and a 1. That's a pretty large capacitor for like in the scheme of things. So that would be a kind of an expensive capacitor. So I'm going to hook that up. I'm going to come over here. I'm going to hook these up to this. And then, did anyone catch what I did wrong just then?
You didn't label.
Yep, I didn't do that. I also didn't offset them. I told myself I was going to, and then I didn't.
Put them at the thing.
Yeah, I put them at the same thing. So when you come here and you're trying to find the resistance, right? You look at that graph. You'll find the linear region. So let's say like right here in the middle, and then you'll just draw a line straight down, 4 volts, 3.9 volts, something like that. And then you're gonna do a really simple voltage divider. So uh, you guys see if this works. Cool. You can see that.
Your goals only send 3.9 volts to the right hand side.
Yeah. Yeah, right hand side meaning to the MOSFET. Yeah, exactly. So I have my voltage source here. It's 10 volts. I have my upper resistor. I have my MOSFET that's also hooked up to the right there. Yep, you got it. We're calculating that. Yeah, this resistor, I think it was 10 ohms. What's up? Yeah, I can add that in here, for like posterity's sake, but it doesn't really matter for the calculations that we're gonna be doing. Okay, so we set this to be 3.9 volts, right?
Yep.
Right here, we have 10 volts, right? So that means that we need to drop what is that, 6.1 volts across this resistor. In order to do that, you're gonna send like a certain amount of current through it, right? But the easiest way of doing that is just to like figure out the ratio of the two resistors in relation to each other. And that would just be what, like 10 divided by 3.9. Yeah. So whatever that is. So 2.56 is the number I'm coming up with here. So that means that this resistor on the top needs to be 2.56 times larger than this resistor down here. A really easy way of doing that would just be to make this 1 kilo ohm, kind of picking that at random. And then the top one, I would just pick 2.56 kilo ohms. And then but you do some calculations to like confirm that. So pretty easy one would just be V equals IR, right? We know we have 10 volts at the top, so that would be 10. We know we have 1 kilo ohm on the bottom here, and then 2.56 kilo ohms on the top there, so that would be 3.56 K. And then we can solve for I, so that'd be 10 divided by 3,560. So that means that we have amps. What is that? 2.8 milliamps. And then once we know that, then we can just multiply this 2.8. Damn, my calculations are wrong. Multiply that 2.8 milliamps times the 1000 of the bottom resistor, and then you end up with the V equals IR again. R is 1000, I is I, so that's 2.8 milli. V equals, and then you can be like, oh, well, shit, that's only 2.8 volts. So I did my math wrong.
You mean 2.56, not 3.56?
Well, I'm gonna be getting the total amount of current flowing through this entire chain here.
Oh.
So I would have had to take that into account in my calculations up here. So what we can do really simply is we can make this, instead of a 2.56, I'm gonna make that 1.56. And then I'm going to rerun my calculations real quick. So that would be 10 divided by 2,560. That's 3.9 milliamps. So I'm gonna bring that down here. 3.9 milli times 1,000. And there you go. 3.9 volts. So that means I have to change this 2.56 to 1.56, and that's it. Now your transistor is biased into that linear zone. Did that make sense to like anybody? A little bit.
Where's that 3.9 volts? Or like
Yeah, good question. So 3.94, wait, 3.9, right? Yeah, 3.9 is just looking at this line, like literally just with my eyeballs. And then taking this point in the center of that green line, and then just drawing it down to roughly there. Sorry, I know you can't see this, but this is 4 volts. So anywhere between like this point and like this point would be pretty okay. So 3.9 was kind of in the center of that.
Was just somewhere in the middle of that.
Yeah, in the linear region.
Okay.
Yeah, good question.
Why needs to be linear?
Yeah. I'll show you guys actually in a second what happens if it's not in the linear region. But it needs to be in the linear region here because if it's not, then when you increase this line right here, this red line, can you see the red line? Okay, sick.
Yeah, a little bit.
A little bit. Sure. So when you take this input and instead of a line, you have a sinusoid. So essentially that means that your voltage, instead of just going from here up to there once, it'll be going back and forth up and down this line. This is a really terrible way of explaining this.
So what will happen when we rectify it in our case?
So this isn't a rectifier circuit. I can show you a rectifier circuit.
Well, we added go back to the graph.
Mhm.
We added the capacitor and resistors.
Yes.
What should happen to the current after we've added those?
In theory, if that voltage source doesn't do anything, if it's a DC voltage source, it'll look exactly like this. It'll just give you a single voltage output right at this point. I know that doesn't make a lot of sense.
And what would happen to the current?
The current would give you a single current value. So
Okay.
yeah, it would just always be a constant output instead of a sweep. Because right now we're sweeping the input parameters, but we're picking a point here. So you would end up with a single voltage and a single current on the output.
So the voltage is gonna go back and forth because it's a sinusoidal, so you wanna pick something that's generally for it's closer to the straightest part.
Yes.
Question about the circuit, so those two resistors that you added, they're in series, right?
Yes.
How
How are they in series?
Yeah, it's like they don't really share a common code, right? They're like linear.
They're not in series.
No, they're in series.
Yeah.
No, because
Because like
R2 is in parallel with your MOSFET, and R3 is in parallel with C1 and DC, so they're not in series.
In relation to each other, they are. I think I should explain one more thing. So imagine that I only have DC in this circuit, right? What does the capacitor look like in DC?
Well, at least, so it technically, yeah, the capacitor is.
Okay, so that one's open. So you see this line right here?
Yeah.
And you see these 3 lines? The reason why it's drawn like that too is because from this perspective, your MOSFET is a capacitor.
Okay, so it would also be open, so yes, it means.
Yes, yeah, exactly. Yeah, so this is one of the reasons why I like working with MOSFETs and not BJTs, is because MOSFETs are that capacitor and no current flows into the gate. Like, an ideal MOSFET, that capacitor is like a really, really, really small capacitance. And so even with AC, no current flows into the gate. You'll learn that's not true later in this class, but in an ideal sense, that's how it is. Yeah. Cool. Other questions? What's up?
I think you finished. So you still good?
Oh. Yeah. I think that'll be easier to explain if I actually simulate it. So you can see what it looks like when it's in that linear region versus when it's not in that linear region. Is that cool with you guys? Okay, sick. Sorry, let me just go back over to my notes. How much time? Oh god, we only have 15 minutes. I have like a couple other things I want to teach you guys, but we'll see how it goes. Okay, sweet. So in order to do a sinusoid here, I'm gonna have to change my V2 and I'm gonna have to change my spice directive. So I'm gonna start with my spice directive. This is a DC sweep. And what I need is a transient. A transient basically just means you're not sweeping any parameters. You're just letting it run in the time domain. So if you're to look at a sinusoid in a transient, it'll just literally look like a sinusoid. Versus in a sweep, it won't. Yep, so that's just .tran and then space and then how long you want it to run. I'm just going to choose 100 milliseconds. And then I'm going to right click on my voltage source and I'm going to go to advanced. That's going to bring up this menu here. I'm going to go to sine. My DC offset, I'm going to do 0. My amplitude, kind of forgot what that linear region looked like here. It's it looks like it's only like 2 volts. So I'm going to do an amplitude of 1 volt because the amplitude isn't peak to peak, it's 1/2 of that sine. And then frequency, I'm going to do 60 hertz because that's what our electrical grid is. I'm going to hit OK. And then I'm going to simulate it. Oh, sorry, I forgot to enter in those MOSFET values, or sorry, those resistor values. 1560. And then this one's just going to be 1000. Yep. Yeah. So this is literally tracking the same stuff as before, but you can see that the sinusoid actually does look pretty clean. It's it doesn't have any like weird distortion at the bottom or at the top. This is like not strictly linear, which is good. You want it to look like a clean sinusoid. So this is what you want it to look like. If I were to change one of those resistor values, let's say I'll make this one pretty small. I'll make this 100 volts. Or sorry, 100 ohms. And then I go ahead and I run it again. That's what it looks like if you don't put it in the linear region. So that would be biasing it at a much lower voltage. You know, instead of, you know how that line was like kind of like this, right? That would be biasing it down on this section over here. And I can show you what happens if I bias it the other direction as well. So I'll put this back to what it was, and then I'll take this and I'll move it just a little bit up to 2000 ohms, and then I'll run it again. This is pretty close to still looking good, and I don't think you can see it because of the heads, but this section right down here is actually squished. It's like up a little bit. Let me make that a little bit more dramatic. Okay, can you see it a little bit more clearly now? This is very rounded and that is very peaky. So that's what happens if it's not like in the linear region. And what this manifests as is harmonic distortion. Your harmonic is the 60 hertz sinusoid, and then the distortion on that is like stubby on the bottom, pointy on the top. Yeah. Yeah, so that's kind of what this manifests as. That's the whole reason. What's up? Yeah, and it just won't be the signal you put into it. Yeah, exactly. Cool. Sorry, I know that was a lot and you're skipping like 3 months of coursework to get to this point. Any questions? Any questions with the software itself and how to use it? No? Okay, let me quickly go over the rubric real quick so that you guys can at least see it before I post it later. Is this number 1 or is this 2? Okay, this is number 2. Okay. So I typically make my rubrics like pretty thorough just because it makes it a little bit more fair. And I don't have to think as much, which is great. So a lot of this stuff you'll notice, it's like, did you do it? You get the points. Did you not do it? You don't get the points. Some of it is effort. So explanations, I would expect like 2 to 3 sentences each time it tells you to explain something. If you go more than that, it's kind of a pain for me to read. If you go less than that, you're probably not getting the point across. Make sure your screenshots are easy to read and high contrast. Oh yeah, for the project number 1, I actually included a little bonus section. So if you include something that's not in that library and you import it from LTSpice, or not LTSpice, DigiKey, or if you import it from Mauser, or Infineon or any other manufacturer into LTSpice, and you show me a screenshot of how you do it, you get 5% more on the project. And I'll post these so that you know how you're getting graded. I didn't do that last time and it was not great. There's a big ass table at the very end. I feel like that's a really good learning opportunity. It's like 11% of your project. Yeah, I'll post these guys. Oh, and then I'll also post these notes. It includes some like really solid MOSFETs and diodes that you can use. Sorry, just one more second. Oh, do you guys mind if I show you one more circuit that's already done? Okay. So this guy is a really basic circuit. You won't, I don't think you guys have to do this, but it shows the functionality of the diode really well. So I wanted to show it to you. So I'm just going to pull up a scope here and I'm going to look at the current of the diode. Oops, my bad. There you go. So this is just a 60 hertz sinusoid, and you can see that on the top half because when you have voltage here that's positive, it'll flow current. But when this thing inverts on the second half of that sinusoid, it'll try and send current the back way through the diode. And you can see here that as soon as it hits 0 volts, it won't give you that second half. And that's kind of what a sinusoid sent through a diode looks like. Does that kind of make sense? Does that give you like a little bit of intuition for the diodes? Okay, say, because that's, unless you're biasing like an LED, this is basically all you need to know about diodes, especially in 310. If any of you guys are taking 310, what's up?
The sweep is for that's area of the voltage and the amps.
Yeah.
Right, and the transfer is just amps and time.
Yep. Yeah. So the sweep, the DC sweep is in the God, I don't know what domain that would be. It would be like the DC sweep domain. And then the transient is time domain. So that's what you would, if you're scoping something in real life, you would see the DC sweep. I also included a little section at the top here for an AC sweep. You definitely can't see that either. And the AC sweep will put you in the frequency domain. So if you're an electrical engineer, you'll be spending a ton of your time in the frequency domain. When you do an AC sweep, you'll be in the frequency domain. Yeah. So that's basically just like that AC sinusoid voltage source, instead of just being at 60 hertz, it'll run the simulation like thousands of times. Let's say at 1 hertz, at 2 hertz, at 3 hertz. And then at each one of those points, it'll plot your response. So in this case, it's voltage. You can plot your gain. That's a really useful one. Yeah. And then, yeah, I'll share this resource with you guys too. I'll share the rubrics tonight. And then I'll share this Zoom whenever it's done processing, and hopefully you guys can hear me. What's up?
Is that campus?
It will be. It will be, yeah. I think the Zoom takes like 5 hours to process, and it'll send me a notification. Once it sends me a notification, I'll post it, the rubrics, and this like document that you see here. Yeah. Cool. Yeah, any other questions? None? Okay. I'll be here when you guys take your exams. I'll be here during a guest lecture towards the end of the semester. Other than that, I don't think you'll really see me too much, but yeah, good luck.